Picture this. You're sitting in traffic on a Tuesday morning, watching the minutes tick by as your commute stretches into what feels like an eternity. Now imagine if instead of being stuck behind that slow-moving truck, you could simply warp the fabric of space and time itself, arriving at your destination before you even left. This isn't just the stuff of science fiction anymore. Real physicists are seriously exploring whether we could one day bend the universe to our will and travel faster than light itself. Tonight, we're diving deep into one of the most mind-bending concepts in modern physics: the science behind warp drives, and whether humanity might actually crack the code to faster than light travel. Before we embark on this journey through space-time itself, I'd love to know where you're watching from and what keeps you fascinated by the mysteries of the cosmos. And if you find yourself drawn to these explorations of cutting-edge science, I'd be grateful if you gave this video a like and perhaps subscribe to join our community of scientific adventurers. Get ready. The journey begins now. What I'm about to share with you will fundamentally change how you think about travel, distance, and the very nature of reality itself. We're not talking about building faster rockets or more efficient engines. We're talking about something far more profound and revolutionary. We're talking about manipulating the basic structure of the universe to make impossible journeys possible. In 1994, a Mexican physicist named Miguel Alcubierre published a paper that sent shockwaves through the scientific community. Working at the University of Wales, Alcubierre wasn't trying to revolutionize space travel. He was simply exploring the mathematical consequences of Einstein's field equations when he stumbled upon something extraordinary, something that suggested faster than light travel might not violate the laws of physics after all. The key insight that Alcubierre discovered lies in understanding what we really mean when we talk about the speed of light limit. Einstein's special relativity tells us that nothing can travel through space faster than light. But here's the crucial detail that most people miss. Einstein's general relativity, his theory of gravity and space-time, doesn't place any limits on how fast space itself can expand or contract. Think about it this way. If you're walking on a moving walkway at the airport, your speed relative to the terminal isn't just how fast you're walking. It's your walking speed plus the speed of the walkway itself. Now imagine if instead of a walkway, you could control the expansion and contraction of space itself. You could remain stationary relative to your local piece of space-time, while that space-time carries you to your destination faster than light could travel through normal space. This is the fundamental principle behind what we now call the Alcubierre warp drive. Instead of pushing a spacecraft through space at incredible speeds, you warp space itself. You create a bubble of curved space-time where space contracts in front of your ship and expands behind it. The ship itself never exceeds the speed of light relative to its local space-time, but the expansion and contraction of space can carry it across vast distances in impossibly short times. The mathematics of this concept are as beautiful as they are complex. Alcubierre's metric, as physicists call it, describes exactly how space-time would need to be curved to create this effect. The metric is essentially a mathematical recipe that tells us how to warp the geometry of space and time to achieve faster than light travel without violating relativity. When you dive into the equations, what emerges is something that looks almost magical. The Alcubierre metric describes a space-time geometry where you create what physicists call a warp bubble. Inside this bubble, space and time behave normally. A passenger in the spacecraft would experience no unusual forces, no time dilation, no uncomfortable accelerations. They would simply sit in their chair while the universe rearranges itself around them. But outside the bubble, space-time becomes dramatically warped. In front of the spacecraft, space contracts, bringing distant objects closer. Behind the spacecraft, space expands, pushing the starting point farther away. The net effect is that the ship surfs on a wave of expanding and contracting spacetime, potentially crossing interstellar distances in days or weeks, rather than thousands of years. The beauty of this approach is that it sidesteps the fundamental problems that plague conventional faster-than-light travel schemes. You don't need infinite energy to accelerate matter to light speed because you're not accelerating the matter at all. You don't experience deadly time dilation effects because time flows normally inside the warp bubble. You don't get compressed into a pancake by relativistic forces because you're not experiencing any acceleration relative to your local spacetime. From the perspective of someone inside the warp bubble, the journey would be remarkably peaceful. You could look out the window and watch stars slide past as space itself carries you between worlds. The trip to Alpha Centauri, normally a journey of over 4 light years, could potentially be completed in a matter of days. A voyage to the center of our galaxy, typically requiring 26,000 years at light speed, might take just months. But here's where the dream meets the harsh realities of physics. Creating an Alcubierre warp drive requires something that might not exist in our universe, something so exotic and strange that it challenges our understanding of matter and energy themselves. To understand this challenge, we need to dive deeper into what the mathematics actually demand. When physicists analyze the Alcubierre metric, they find that creating the required space-time curvature demands a very specific type of matter. Not the ordinary matter that makes up stars, planets, and everything we see around us. Something far more exotic. The mathematics reveal that warp drive technology requires what physicists call exotic matter. This isn't exotic in the sense of being rare or expensive. It's exotic in a much more fundamental way. Exotic matter has negative energy density, meaning it has less energy than empty space itself. This might sound impossible, but quantum mechanics suggests that such matter might actually exist under very specific circumstances. Think about empty space, what physicists call the quantum vacuum. According to quantum field theory, this apparently empty space is actually seething with activity. Virtual particles constantly pop into existence and annihilate each other in timescales so brief that they don't violate conservation of energy. These quantum fluctuations give empty space a baseline energy level. Exotic matter would have an energy density below this baseline. It would have negative pressure, negative mass, and would interact with gravity in ways that seem to defy common sense. Instead of attracting other matter gravitationally, exotic matter would repel it. Instead of being attracted to massive objects, it would be pushed away from them. The amount of exotic matter required for a practical warp drive is staggering. Early calculations suggested you would need more exotic matter than exists in the observable universe to power a warp bubble large enough to carry a spacecraft. The energy requirements were so astronomical that they made the concept seem purely theoretical, interesting as a mathematical curiosity, but impossible to implement practically. However, the story doesn't end there. In the decades since Alcubierre's original paper, physicists have found ways to dramatically reduce these energy requirements. Chris van den Broek, a physicist at the Catholic University of Leuven, discovered that by carefully shaping the warp bubble, you could reduce the exotic matter requirements by many orders of magnitude. Van den Broek's insight was to create a warp bubble with a very thin wall and a much smaller interior space. Instead of needing exotic matter equivalent to the mass of Jupiter, his design might require only a few hundred kilograms. Still an enormous challenge, but no longer physically impossible in principle. Further refinements by other physicists have continued to chip away at the energy requirements. Harold White at NASA's Johnson Space Center proposed modifications to the Alcubierre geometry that could reduce the exotic matter requirements even further. By oscillating the warp bubble's intensity and carefully shaping its geometry, White's calculations suggest the energy requirements might drop to levels that could theoretically be achieved with advanced future technology. These developments have transformed warp drive research from pure mathematics into something that aerospace engineers are beginning to take seriously. NASA has funded preliminary research into warp drive physics. The Pentagon has acknowledged studying what they call advanced aerospace propulsion systems that might include warp drive concepts. Private companies and research institutions around the world are exploring the theoretical foundations of spacetime manipulation. But even with these improvements, enormous challenges remain. The exotic matter required for warp drives has never been created in laboratory conditions. We have theoretical reasons to believe it might exist based on quantum field theory and our understanding of the Casimir effect. But producing macroscopic quantities of exotic matter remains far beyond our current capabilities. The Casimir effect demonstrates that negative energy densities can exist in very specific circumstances. When you place two perfectly flat, parallel metal plates very close together in a vacuum, quantum fluctuations create a region of negative energy density between the plates. The plates experience a small but measurable attractive force as a result of this negative energy. This proves that exotic matter isn't just a mathematical abstraction. It exists, at least on microscopic scales, and under carefully controlled conditions. The challenge is scaling this effect up to the quantities and configurations needed for warp drive technology. Some physicists have proposed alternatives to exotic matter that might achieve similar effects. These include manipulating dark energy, the mysterious force causing the universe's expansion to accelerate, or finding ways to create negative mass using advanced quantum engineering techniques. The scientific debates surrounding warp drives are as fascinating as the physics itself. Some physicists argue that the energy requirements, while reduced from Alcubierre's original calculations, remain prohibitively large. Others question whether exotic matter can exist in the stable configurations required for warp drive operation. There are also causality concerns. If warp drives allow faster-than-light travel, they might also enable time travel to the past, creating logical paradoxes that could threaten the consistency of physics itself. Some physicists argue that unknown quantum effects or fundamental principles might prevent warp drives from functioning, even if all the classical physics requirements are met. Stephen Hawking proposed what he called the chronology protection conjecture, suggesting that the laws of physics somehow prevent the creation of closed time-like curves that would allow paradoxical time travel. If warp drives could enable such paradoxes, Hawking's conjecture implies that some unknown physical principle would intervene to prevent their operation. Despite these challenges and debates, research into warp drive physics continues to advance. Scientists are exploring new mathematical formulations, investigating alternative spacetime geometries, and searching for ways to create and manipulate exotic matter in laboratory settings. The implications of successful warp drive development would be revolutionary beyond anything in human history. We could establish colonies on distant worlds, explore other star systems, and potentially make contact with alien civilizations if they exist. The economic, social, and philosophical impacts would reshape human civilization in ways we can barely imagine. But we're still in the very early stages of understanding whether warp drives are physically possible, let alone practical to build. The mathematics work beautifully on paper, but translating mathematical elegance into engineering reality has always been one of science's greatest challenges. What makes this field so exciting is that we're not just dealing with distant high-height theoretical possibilities. Every year brings new insights into the nature of spacetime, exotic matter, and quantum field theory. Advanced particle accelerators, space-based telescopes, and precision measurement devices are providing new data that helps us understand whether the universe allows the kind of spacetime manipulation that warp drives require. The journey from Alcubierre's original paper to practical warp drive technology may take decades or centuries, but the fundamental question has shifted from whether faster than light travel is possible in principle, to whether we can develop the engineering capabilities to make it reality. As we delve deeper into the mechanics of warp drive physics, we encounter mathematical structures so elegant they seem almost too beautiful to be describing real phenomena. The Alcubierre metric isn't just a theoretical curiosity tucked away in dusty physics journals. It's a precise mathematical description of how space-time itself would need to behave to carry us between the stars. To understand what makes this metric so remarkable, we need to think about space-time as something malleable, something that can be shaped and molded like clay in the hands of a cosmic sculptor. Einstein showed us that massive objects naturally warp space-time around them. The sun creates a depression in the fabric of space that causes planets to orbit. Black holes create such extreme warping that they trap light itself. But the Alcubierre metric describes something far more sophisticated than these natural distortions. It's a blueprint for engineering space-time itself, for creating precisely controlled regions where the geometry of space and time bend to our will rather than to the gravitational influence of massive objects. The mathematical beauty of this metric lies in its symmetry. Picture a surfer riding a wave, staying in one position relative to the moving water, while the ocean carries them forward. The Alcubierre metric creates something analogous in space-time itself. The spacecraft remains stationary within its local reference frame, while a wave of expanding and contracting space propels it forward. When you examine the equations closely, you discover that this metric describes a bubble-like distortion in space-time. The bubble has three distinct regions, each with its own unique properties. At the front of the bubble, space-time contracts, compressing distances and bringing faraway destinations closer. At the rear, space-time expands, stretching the fabric of reality and pushing the point of origin farther away. And in the middle, within the bubble itself, space-time remains completely flat and normal. This three-zone structure is what makes warp drive travel so appealing from an engineering perspective. Passengers inside the bubble would experience no strange gravitational effects, no time dilation, no crushing accelerations. They could walk around their spacecraft normally, eat meals, sleep, and conduct experiments exactly as they would on Earth. Meanwhile, the universe outside would be racing past at speeds that dwarf anything achievable through conventional propulsion. The metric also reveals something profound about the nature of faster-than-light travel itself. We often think about breaking the light speed barrier as pushing through some kind of cosmic wall, like a jet breaking the sound barrier. But the Alcubierre approach is more subtle. You're not breaking any speed limits because you're not technically moving through space at all. Space itself is moving, carrying you along like a passenger on a cosmic conveyor belt. This distinction matters enormously because it sidesteps many of the paradoxes and problems associated with faster-than-light travel in science fiction. When the Enterprise engages warp drive in Star Trek, the writers intuited something remarkably close to real physics. The ship isn't accelerating through space at impossible speeds. It's manipulating the structure of space-time to make distant locations accessible without violating relativistic speed limits. But here's where the elegant mathematics collide with the stubborn realities of engineering. Creating the space-time distortions described by the Alcubierre metric requires us to become master architects of reality itself. We need to learn how to grab the fabric of space and time and twist it into precisely the right configuration. This brings us face to face with one of the most challenging requirements in all of theoretical physics. The energy-momentum tensor in Einstein's field equations tells us exactly what kind of matter and energy distribution would be needed to create the Alcubierre geometry, and the answer is both fascinating and deeply problematic. The calculations reveal that successful space-time engineering demands what physicists call exotic matter. But this term barely captures how strange this substance would need to be. We're not talking about antimatter, which science fiction often portrays as exotic but which actually behaves quite normally under gravitational influence. We're talking about matter that has negative energy density, negative pressure, and gravitational properties that seem to turn physics upside down. To understand why this matters, consider how ordinary matter behaves in the presence of gravity. Drop an apple, and it falls toward Earth because matter with positive energy density creates attractive gravitational fields. Even light bends toward massive objects because photons follow the curved spacetime created by ordinary matter and energy. Exotic matter would do the opposite. It would create repulsive gravitational effects, pushing other matter away rather than attracting it. If you could somehow create a ball of exotic matter and drop it, it would fall upward, accelerating away from Earth rather than toward it. Light passing near exotic matter would bend outward, as if fleeing from something that violates the normal rules of gravitational interaction. This anti-gravitational behavior is precisely what makes exotic matter so valuable for warp drive applications. The contracting spacetime at the front of the warp bubble and the expanding spacetime at the rear both require gravitational effects that ordinary matter simply cannot produce. You need matter that pushes spacetime around in ways that seem to defy common sense. The energy requirements for creating sufficient quantities of exotic matter are where the dream of warp drives confronts its greatest challenge. When Alcubierre first calculated the energy needed to create a warp bubble large enough for a spacecraft, the numbers were astronomically large. Not just expensive or difficult to achieve, but requiring more energy than exists in all the visible stars and galaxies combined. These calculations suggested that you would need exotic matter with a mass-energy equivalent roughly equal to the observable universe itself. Even if exotic matter could somehow be created and controlled, the energy requirements placed warp drives firmly in the realm of impossibility rather than mere difficulty. But science has a way of finding unexpected solutions to seemingly impossible problems. In the years following Alcubierre's original paper, physicists began discovering ways to dramatically reduce these energy requirements through clever modifications to the basic warp drive geometry. The key insight came from recognizing that the size and shape of the warp bubble could be optimized for efficiency. Chris van den Broek showed that by creating a bubble with a very thin wall and a much smaller interior volume, you could achieve the same faster-than-light travel with exponentially less exotic matter. Van den Broek's design resembles a cosmic version of a ship in a bottle. From the outside, the warp bubble would appear relatively small, perhaps only a few meters across, but inside, through careful manipulation of space-time geometry, there would be enough room for a spacecraft and its crew. The exotic matter requirements dropped from universe-sized quantities to something more like the mass of a planet, still impossibly large by current standards, but no longer requiring more energy than exists in all of creation. This reduction transformed warp drives from mathematical impossibilities into theoretical possibilities that might someday become engineering challenges. Further refinements have continued to chip away at the energy requirements. Harold White at NASA proposed oscillating the intensity of the warp field, creating a kind of pulsed warp drive that might require even less exotic matter. By carefully timing these oscillations and shaping the bubble geometry, White's calculations suggested the exotic matter requirements might drop to hundreds of kilograms, rather than planetary masses. These improvements have sparked serious interest from aerospace engineers and government research programs. NASA's Advanced Propulsion Physics Laboratory has funded preliminary studies into warp drive feasibility. The Pentagon's Advanced Aerospace Threat Identification Program has acknowledged investigating advanced aerospace propulsion systems that might include space-time manipulation technologies. Private research institutions and universities around the world are exploring the theoretical foundations of exotic matter creation and space-time engineering. What began as a mathematical curiosity in Alcubierre's office has evolved into a legitimate field of research that bridges theoretical physics with practical engineering concerns. The scientific debates surrounding these developments are as intense as they are fascinating. Physicists are deeply divided on whether exotic matter can exist in the stable macroscopic quantities required for warp drive operation. Some argue that quantum mechanical effects or unknown physical principles might prevent the creation of large-scale exotic matter structures. Others point to phenomena like the Casimir effect as proof that negative energy densities are not just theoretical abstractions but real, measurable aspects of quantum field theory. The Casimir effect demonstrates that when you place two metal plates very close together in a vacuum, quantum fluctuations create a region of negative energy density between them, producing a small but detectable attractive force. This effect proves that exotic matter, at least in microscopic quantities and under carefully controlled conditions, actually exists in our universe. The question becomes whether these quantum mechanical phenomena can be scaled up and harnessed for macroscopic applications like warp drives. Some researchers are exploring alternative approaches that might sidestep the exotic matter requirement entirely. These include proposals for manipulating dark energy, the mysterious force driving the accelerating expansion of the universe, or finding ways to create effective negative mass through advanced quantum engineering techniques. The debates extend beyond just the technical feasibility of exotic matter creation. Some physicists worry about the causality implications of faster-than-light travel. If warp drives allow you to travel faster than light, the mathematics of relativity suggest they might also enable time travel to the past, creating logical paradoxes that could threaten the consistency of physics itself. Stephen Hawking addressed this concern with his chronology protection conjecture, proposing that the laws of physics somehow prevent the creation of closed time-like curves that would allow paradoxical time travel. If warp drives could enable such paradoxes, Hawking's conjecture suggests that some unknown physical principle would intervene to prevent their operation. Other physicists argue that these causality concerns, while theoretically interesting, shouldn't stop us from pursuing warp drive research. They point out that many breakthrough technologies initially seemed to violate established principles before we developed better understanding of the underlying physics. The quantum mechanical aspects of warp drive operation add another layer of complexity to these debates. Some researchers suggest that quantum effects near the warp bubble boundary might create instabilities that prevent stable warp field formation. Others propose that quantum corrections to the classical Alcubierre geometry might actually make warp drives easier to create, rather than harder. These scientific discussions are taking place against the backdrop of rapid advances in our understanding of fundamental physics. New discoveries in quantum field theory, cosmology, and high-energy physics are continuously providing fresh insights into the nature of spacetime, exotic matter, and the quantum vacuum. The Large Hadron Collider and other particle accelerators are probing energy regimes where exotic matter effects might become observable. Space-based gravitational wave detectors are providing unprecedented precision measurements of spacetime curvature. Advanced telescopes are revealing new information about dark energy and the large-scale structure of the universe. Each of these experimental advances brings new data that helps us understand whether the universe permits the kind of spacetime manipulation that warp drives require. We're moving from pure theoretical speculation toward empirical investigation of the physical principles underlying faster-than-light travel. The implications of this research extend far beyond space travel itself. Understanding how to engineer spacetime could revolutionize our approach to energy generation, materials science, and even fundamental questions about the nature of reality. If we can learn to create and control exotic matter, we might unlock technologies that seem like magic by today's standards. But we're still in the very early stages of this scientific revolution. The gap between theoretical possibility and practical implementation remains enormous. Even the most optimistic projections suggest that working warp drive technology, if it's possible at all, lies decades or centuries in the future. What makes this field so compelling is that we're not just dealing with abstract mathematics divorced from experimental reality. Every year brings new theoretical insights, better experimental techniques, and deeper understanding of the physical principles that govern spacetime itself. We're witnessing the birth of an entirely new branch of physics, one that might eventually allow us to reshape reality according to our needs and dreams. The most remarkable aspect of this emerging field is how it's forcing us to reconsider fundamental assumptions about the nature of reality itself. When we talk about spacetime engineering, we're not discussing some distant theoretical possibility. We're exploring technologies that could fundamentally alter the relationship between matter, energy, space, and time in ways that challenge everything we thought we understood about the universe. To grasp the full implications of what physicists are proposing, we need to understand that spacetime isn't some abstract mathematical concept. It's the actual fabric of reality, the stage upon which all physical phenomena play out. When Einstein first described spacetime as a dynamic curved geometry that responds to the presence of matter and energy, he revealed that space and time aren't fixed backdrops for physics, but active participants in every interaction. The Alcubierre metric takes this insight and pushes it to its logical extreme. Instead of simply observing how matter curves spacetime naturally, we're talking about deliberately engineering those curves to achieve specific effects. This represents a transition from being passive observers of cosmic geometry to becoming active architects of reality itself. Consider what this means in practical terms. Right now, if you want to travel from Earth to Mars, you're constrained by the fixed geometry of space. The distance is what it is, and you must either accept the long journey time or build faster rockets. But spacetime engineering offers a third option. Change the geometry itself so that Mars is effectively much closer to Earth than the normal laws of physics would suggest. This isn't cheating or finding loopholes in the laws of nature. It's applying those laws in ways we've never attempted before. Einstein's field equations don't just describe how spacetime curves in response to matter and energy. They provide a complete recipe for creating any desired spacetime geometry, provided you can arrange the right distribution of matter and energy to produce it. The Alcubierre metric is essentially a solution to Einstein's field equations that describes a very specific type of spacetime curvature. When you work through the mathematics, you discover that this particular geometry creates a region where space contracts in front of a spacecraft and expands behind it, while remaining flat and normal in the middle where the crew would be located. The elegance of this solution becomes apparent when you realize that it solves multiple problems simultaneously. Traditional approaches to faster-than-light travel run into seemingly insurmountable barriers, accelerate matter to light speed, and you need infinite energy. Approach light speed and time dilation effects become extreme. Try to exceed light speed through conventional acceleration, and you violate fundamental principles of relativity. But the Alcubierre approach sidesteps all these problems by recognizing that the prohibition against faster-than-light travel applies to motion through space, not to the expansion and contraction of space itself. The spacecraft never violates any speed limits because it's not moving through space at all. Space is moving around it, carrying it along like a leaf on a flowing river. This distinction has profound implications for how we think about interstellar travel. Instead of building ships that can endure decades or centuries of flight between stars, we could potentially create vessels that surf waves of expanding and contracting spacetime, completing interstellar journeys in timeframes measured in weeks or months, rather than millennia. The technical requirements for achieving this kind of spacetime manipulation are where the elegant theory meets harsh engineering realities. Creating the Alcubierre geometry demands precise control over the energy-momentum tensor, the mathematical object that describes how matter and energy are distributed throughout spacetime. In Einstein's field equations, the energy-momentum tensor on one side of the equation determines the spacetime curvature on the other side. If you want to create specific types of curvature, you need to arrange matter and energy in very specific configurations. For the Alcubierre metric, those configurations require something that pushes the boundaries of what we consider physically possible. The exotic matter needed for warp drive operation has properties that seem to violate common sense. Unlike ordinary matter, which has positive energy density and creates attractive gravitational effects, exotic matter has negative energy density and generates repulsive gravitational fields. This isn't just unusual, it's a complete reversal of how we normally think about the relationship between matter and gravity. To understand why this matters, imagine trying to create a hill by digging a hole. In normal circumstances, you can only create elevated terrain by adding material, not by removing it. But exotic matter is like negative dirt. It creates gravitational hills by having less energy than empty space itself. The mathematics work perfectly, but the physical implications challenge our understanding of what matter can be. The energy requirements for creating macroscopic quantities of exotic matter represent one of the most daunting challenges in theoretical physics. When Alcubierre first calculated how much exotic matter would be needed for a practical warp drive, the numbers defied comprehension. We're talking about energy requirements equivalent to converting several solar masses into pure exotic matter. These calculations weren't just pessimistic estimates. They were rigorous mathematical results derived directly from the geometry of the Alcubierre metric. The spacetime curvature required to create the warp bubble effect demands specific amounts of exotic matter distributed in precise configurations. There's no way around these requirements without changing the fundamental geometry of the warp drive itself. That realization sparked a wave of research into alternative warp bubble geometries that might achieve similar effects with more reasonable energy requirements. Van den Broek's breakthrough came from recognizing that the interior volume of the warp bubble could be much smaller than its exterior effect would suggest. By creating a spacetime geometry that's larger on the inside than on the outside, like a cosmic version of a magician's trick, he reduced the exotic matter requirements by many orders of magnitude. Harold White's subsequent refinements pushed the energy requirements even lower by proposing oscillating warp fields that pulse on and off rather than maintaining constant intensity. These modifications suggest that a practical warp drive might require exotic matter quantities measured in tons rather than solar masses. Still an enormous challenge, but no longer requiring more energy than exists in the observable universe. The scientific debates surrounding these developments reveal deep divisions within the physics community about the fundamental nature of reality. Some physicists argue that exotic matter simply cannot exist in the stable, macroscopic quantities required for warp drive operation. They point to quantum mechanical principles that might prevent the creation of large-scale negative energy density configurations. The quantum inequality theorems, developed by physicists studying the limits of negative energy, suggest that nature imposes strict constraints on how much negative energy can exist in any given region of space and for how long. These theorems don't absolutely prohibit exotic matter, but they do suggest that creating the quantities needed for warp drives might be far more difficult than early calculations suggested. Other physicists challenge these pessimistic interpretations by pointing to phenomena like the Casimir effect, which demonstrates that negative energy densities do exist in nature, at least under carefully controlled conditions. When two metal plates are placed very close together in a vacuum, quantum fluctuations create a region between them with less energy than empty space, producing a measurable attractive force. The Casimir effect proves that the quantum vacuum isn't truly empty, but contains a complex structure of virtual particles constantly appearing and disappearing. By manipulating this quantum foam, it might be possible to create regions of negative energy density on larger scales than previously thought possible. Some researchers are exploring whether the same quantum field theory principles that produce the Casimir effect could be scaled up using advanced metamaterials, precisely engineered structures that can manipulate electromagnetic fields in ways that don't occur naturally. These metamaterials might provide a pathway toward creating and controlling exotic matter without requiring completely new physics. The causality concerns raised by faster-than-light travel add another dimension to these scientific debates. If warp drives allow faster-than-light travel, they might also enable time travel to the past, creating logical paradoxes that could threaten the consistency of physics itself. Some physicists argue that these causality problems represent fundamental barriers that nature uses to prevent faster-than-light travel, regardless of our technological capabilities. Stephen Hawking's chronology protection conjecture suggests that the universe somehow prevents the creation of closed time, like curves that would allow paradoxical time travel. According to this idea, any attempt to create a warp drive would be thwarted by quantum effects or unknown physical principles that preserve the normal flow of cause and effect. Other physicists contend that causality concerns, while intellectually interesting, shouldn't prevent us from pursuing warp drive research. They argue that many breakthrough technologies initially appeared to violate established principles before we developed better understanding of the underlying physics. The apparent paradoxes might resolve themselves once we gain deeper insight into the quantum mechanical aspects of spacetime manipulation. The quantum mechanical dimensions of warp drive physics introduce complexities that weren't apparent in Alcubierre's original classical analysis. When you account for quantum field theory effects near the boundaries of the warp bubble, the mathematics become extraordinarily complex. Some calculations suggest that quantum corrections might destabilize the warp field, preventing it from forming or maintaining coherence. But other quantum mechanical effects might actually help rather than hinder warp drive development. The dynamic Casimir effect, which occurs when the geometry of space is changing rapidly, might provide a mechanism for generating the exotic matter needed for warp field creation. Instead of requiring pre-existing exotic matter, a properly designed warp drive might be able to bootstrap itself by using the changing spacetime geometry to create its own exotic matter supply. These quantum considerations are driving researchers toward increasingly sophisticated mathematical models that attempt to capture both the classical general relativistic effects and the quantum field theory corrections. The resulting equations are so complex that they require advanced computational methods to solve, pushing the boundaries of both theoretical physics and applied mathematics. The experimental aspects of warp drive research are evolving from pure theoretical speculation toward laboratory investigations of the underlying physical principles. While we can't yet create macroscopic warp fields, we can study the quantum mechanical effects that might be relevant to exotic matter creation and spacetime manipulation. Precision measurements of the Casimir effect are providing detailed information about how quantum fields behave in curved spacetime geometries. These experiments are revealing subtle effects that weren't predicted by early theoretical models, suggesting that our understanding of quantum field theory in curved spacetime is still incomplete. High-energy particle accelerator experiments are probing regimes where exotic matter effects might become observable. While these experiments can't create the massive quantities of exotic matter needed for warp drives, they can test whether the fundamental principles underlying exotic matter creation are consistent with observed physics. Gravitational wave detectors, like LIGO and Virgo, are providing unprecedented precision measurements of spacetime curvature, revealing details about how gravity propagates and interacts with matter. These observations are testing general relativity in extreme regimes and might eventually detect signatures of exotic matter or spacetime engineering if such phenomena occur naturally in the universe. The technological implications of successful warp drive development extend far beyond space travel. Learning how to engineer spacetime could revolutionize energy production, materials science, and our fundamental approach to manipulating matter at the quantum level. If we can create and control exotic matter, we might unlock capabilities that seem impossible by today's standards. Consider the potential applications of controlled spacetime curvature. You might be able to create regions of altered time flow, where processes could be accelerated or slowed relative to the outside world. You might develop new approaches to energy storage by creating pockets of negative energy density. You might even find ways to manipulate inertia itself, creating materials that resist acceleration in some directions while allowing free movement in others. These possibilities remain highly speculative, but they illustrate why warp drive research is attracting interest from fields far beyond aerospace engineering. The fundamental principles underlying spacetime manipulation could transform our understanding of physics and open up technological possibilities we can barely imagine. The timeline for practical warp drive development remains highly uncertain. Even the most optimistic projections suggest that working prototypes, if they're possible at all, lie decades in the future. The challenges involved in creating and controlling exotic matter, engineering precise spacetime geometries, and solving the quantum mechanical stability problems are formidable by any measure. But the theoretical foundations are becoming increasingly solid. Each year brings new insights into the nature of spacetime, exotic matter, and quantum field theory. Advanced computational methods are allowing researchers to explore warp drive geometries with unprecedented precision. Experimental techniques are providing new data about quantum effects in curved spacetime. The field has evolved from Alcubierre's original mathematical curiosity into a legitimate area of research that bridges theoretical physics with engineering applications. Government agencies, private research institutions, and universities around the world are investing resources in understanding whether the universe permits the kind of spacetime manipulation that warp drives require. What makes this research particularly compelling is its connection to some of the deepest questions in fundamental physics. Understanding exotic matter could provide insights into the nature of dark energy, the mysterious force driving the accelerating expansion of the universe. Learning how to engineer spacetime might reveal new principles about the relationship between quantum mechanics and gravity. The quest to develop warp drive technology is pushing us toward a more complete understanding of reality itself. Whether or not we ever build working warp drives, the journey is expanding our knowledge of physics in ways that will likely have profound implications for future technology and our understanding of the cosmos. As we stand at the threshold of potentially revolutionary discoveries about the nature of space and time, we're confronted with possibilities that would have seemed like pure fantasy just decades ago. Just decades. The mathematics are becoming clearer, the experimental techniques more sophisticated, and our theoretical understanding deeper with each passing year. The dream of faster-than-light travel is transforming from science fiction into serious scientific investigation, driven by rigorous mathematics and supported by increasingly sophisticated experimental capabilities. Whether humanity will ultimately master the art of spacetime engineering remains an open question, but we're closer to answering it than ever before in our history. The profound implications of spacetime engineering become even more apparent when we examine how the Alcubierre metric would actually function in practice. This isn't simply a matter of building a more powerful engine or developing better materials. We're talking about fundamentally altering the relationship between matter, energy, space, and time in ways that would make us architects of reality itself. When physicists first began analyzing the Alcubierre metric in detail, they discovered something remarkable about its mathematical structure. The metric describes a space-time geometry that's essentially three-dimensional origami unfolding and reshaping the fabric of reality in precisely controlled ways. The front of the warp bubble contracts space, effectively bringing distant objects closer. The rear expands space, pushing the point of origin farther away. And in the middle, space-time remains perfectly flat and undisturbed. This three-zone configuration solves what physicists call the passenger problem. In most faster-than-light travel scenarios, the forces required to accelerate matter beyond light speed would instantly vaporize any spacecraft and crew. But inside an Alcubierre bubble, passengers experience no acceleration forces whatsoever. They could conduct delicate scientific experiments, enjoy meals, or sleep peacefully while the universe rearranges itself around them at impossible speeds. The mathematics reveal something even more extraordinary about the nature of this travel. From the perspective of someone inside the warp bubble, the journey occurs in normal time. A trip to Proxima Centauri might take several weeks of subjective time for the crew, during which they age normally and experience the passage of time just as they would on Earth. Meanwhile, outside observers would see the spacecraft crossing 4 light-years of space in those same weeks, apparently violating every known principle of relativity. This temporal consistency eliminates many of the paradoxes that plague other faster-than-light travel concepts. There's no time dilation to worry about, no relativistic aging effects, no need to synchronize clocks across vast distances. The warp bubble creates its own pocket of normal spacetime that travels as a unit through the larger cosmic geometry. But creating this pocket of engineered spacetime requires us to solve what might be the most challenging materials science problem in the history of physics. The exotic matter needed for warp drive operation isn't just unusual or expensive to produce. It represents a fundamental challenge to our understanding of what matter can be. To grasp why exotic matter is so problematic, consider how ordinary matter behaves in gravitational fields. Drop a rock and it falls toward Earth because matter with positive energy density creates attractive gravitational effects. This attraction is what holds planets in orbit around stars, keeps galaxies bound together, and shapes the large-scale structure of the universe. Every form of matter and energy we've ever encountered, from hydrogen atoms to black holes, follows this same pattern. Exotic matter breaks this universal rule. It has negative energy density, meaning it contains less energy than completely empty space. This creates repulsive rather than attractive gravitational effects. If you could somehow create a ball of exotic matter and release it near Earth, it would accelerate upward, fleeing from our planet's gravitational field rather than being attracted to it. The implications extend far beyond simple gravitational repulsion. Exotic matter would bend light rays outward rather than inward, creating optical effects that seem to violate causality. It would interact with electromagnetic fields in ways that could fundamentally alter the behavior of atoms and molecules. Most importantly for warp drive applications, it would curve spacetime in the precise manner needed to create the Alcubierre geometry. The energy requirements for producing macroscopic quantities of exotic matter initially appeared to make warp drives physically impossible. When Alcubierre first calculated the exotic matter needed for a warp bubble large enough to carry a spacecraft, the numbers were beyond astronomical. We're talking about negative energy densities equivalent to the mass energy of multiple solar systems, distributed with incredible precision throughout the warp field geometry. These weren't pessimistic estimates based on inefficient technology. They were fundamental requirements derived directly from Einstein's field equations. The spacetime curvature described by the Alcubierre metric demands specific amounts of exotic matter in precise configurations. There's no way to cheat or find shortcuts without changing the basic physics of how warp bubbles would operate. The breakthrough came when physicists realized that the geometry of the warp bubble could be optimized for efficiency. Chris van den Broek's insight was revolutionary in its simplicity. Instead of creating a large, inefficient warp bubble, why not design one that's much smaller on the outside, but larger on the inside. This dimensional manipulation, achieved through careful spacetime engineering, could reduce exotic matter requirements by factors of billions or trillions. Van den Broek's design resembles a cosmic version of architectural trickery, like creating a building that appears modest from the street but contains vast interior spaces. The warp bubble would appear relatively small to external observers, perhaps only a few dozen meters across, but inside, through precise manipulation of spacetime geometry, there would be ample room for a spacecraft, crew, and cargo. This geometric optimization reduced the exotic matter requirements from solar system scale quantities to something more manageable, though still enormous by any practical standard. Instead of needing exotic matter equivalent to the mass of Jupiter, Van den Broek's design might require only planetary scale quantities, still impossible with current technology, but no longer requiring more energy than exists in the observable universe. Harold White's subsequent refinements pushed the energy requirements even lower through dynamic field manipulation. His oscillating warp drive concept proposes pulsing the exotic matter field on and off in carefully timed sequences, like a cosmic strobe light that creates the illusion of continuous motion through rapid alternation. This approach could potentially reduce exotic matter requirements to thousands of tons rather than planetary masses. White's calculations suggest that by oscillating the warp field at specific frequencies and carefully shaping the bubble geometry, the energy requirements might drop to levels that advanced future civilizations could theoretically achieve. We're still talking about energy expenditures that dwarf anything in human experience, but the numbers have moved from impossible to merely extraordinarily difficult. These theoretical advances have attracted serious attention from aerospace engineers and government research programs. NASA's Breakthrough Propulsion Physics program has funded preliminary studies into warp drive feasibility. The Advanced Aerospace Threat Identification program has acknowledged investigating propulsion systems that might include spacetime manipulation technologies. Universities and private research institutions worldwide are exploring the theoretical foundations of exotic matter creation and controlled spacetime engineering. But significant scientific debates continue to rage about whether these optimized warp drive designs could actually function in practice. Some physicists argue that quantum mechanical effects would destabilize any attempt to create macroscopic exotic matter structures. The quantum inequality theorems suggest that nature imposes strict limits on how much negative energy can exist in any region and for how long. These quantum constraints don't absolutely prohibit exotic matter creation, but they do suggest that maintaining stable warp fields might be far more difficult than classical calculations indicate. Virtual particle fluctuations in the quantum vacuum might interfere with exotic matter configurations, causing warp bubbles to collapse or become unstable within microseconds of formation. Other physicists challenge these pessimistic interpretations by pointing to natural phenomena that demonstrate negative energy effects. The Casimir effect, observed in countless laboratory experiments, proves that regions of negative energy density can exist between closely spaced metal plates. While these effects operate on microscopic scales, they demonstrate that exotic matter isn't merely a mathematical abstraction, but a real feature of quantum field theory. Recent research into metamaterials and engineered quantum systems suggests possible pathways towards scaling up Casimir-like effects. By creating precisely structured materials that manipulate electromagnetic fields in unnatural ways, researchers might be able to generate negative energy densities on larger scales than previously thought possible. These approaches could provide stepping stones toward the exotic matter production techniques needed for warp drive applications. The causality implications of faster-than-light travel add another layer of complexity to these debates. Einstein's relativity theory demonstrates that faster-than-light travel and communication could enable time travel to the past under certain circumstances. If you can travel faster than light, you might be able to send messages to your own past, creating logical paradoxes that seem to threaten the consistency of physics itself. Stephen Hawking addressed this concern with his chronology protection conjecture, proposing that unknown physical principles prevent the creation of time travel paradoxes. According to this idea, any attempt to build a device that could cause temporal paradoxes would be automatically prevented by quantum effects or other natural mechanisms we don't yet understand. Some physicists argue that these causality concerns represent fundamental barriers to faster-than-light travel, regardless of our technological capabilities. They suggest that the universe has built-in protections against paradox creation that would prevent warp drives from functioning even if all the energy and exotic matter requirements could be met. Others contend that causality problems might resolve themselves through better understanding of quantum gravity and the relationship between space-time geometry and information theory. They point out that many revolutionary technologies initially appeared to violate established physical principles before we developed more complete theoretical frameworks to understand them. The quantum mechanical aspects of warp drive operation introduce mathematical complexities that weren't apparent in Alcubierre's original analysis. When you account for quantum field theory effects near the boundaries of warp bubbles, the calculations become extraordinarily intricate. Virtual particles, vacuum fluctuations, and quantum corrections to the classical spacetime geometry all play roles that could either stabilize or destabilize warp field formation. Some researchers suggest that quantum effects might actually help warp drive operation rather than hindering it. The dynamic Casimir effect, which occurs when spacetime geometry changes rapidly, might provide a mechanism for generating exotic matter as the warp field forms. Instead of requiring pre-existing exotic matter supplies, a properly designed warp drive might bootstrap itself by using changing geometry to create its own exotic matter. These quantum considerations are driving research toward increasingly sophisticated theoretical models that attempt to capture both general relativistic and quantum field theory effects simultaneously. The resulting mathematics are so complex that they require advanced computational methods and supercomputer simulations to solve, pushing the boundaries of both theoretical physics and applied mathematics. Experimental investigations of warp drive physics are evolving from pure theoretical speculation toward laboratory studies of underlying physical principles. While we can't yet create macroscopic warp fields, researchers can study quantum effects that might be relevant to exotic matter creation and spacetime manipulation on smaller scales. Precision measurements of the Casimir effect are revealing subtle details about how quantum fields behave in curved spacetime geometries. These experiments are uncovering effects that weren't predicted by early theoretical models, suggesting that our understanding of quantum field theory in engineered spacetime remains incomplete. Particle accelerator experiments are probing energy regimes where exotic matter effects might become observable. While these facilities can't produce the massive quantities of exotic matter needed for spacecraft propulsion, they can test whether the fundamental principles underlying exotic matter creation are consistent with observed physics. Gravitational wave detectors are providing unprecedented precision measurements of spacetime curvature and how gravitational fields propagate through the universe. These observations test general relativity in extreme conditions and might eventually detect signatures of natural spacetime engineering if such phenomena occur in cosmic environments. The technological implications of successful spacetime engineering extend far beyond interstellar travel. Mastering the creation and control of exotic matter could revolutionize energy production, materials science, and our fundamental approach to manipulating matter at quantum scales. If we can engineer spacetime geometry, we might develop capabilities that seem magical by current standards. Controlled spacetime curvature could enable the creation of regions with altered time flow, where industrial processes could be accelerated or slowed relative to the external world. Negative energy density configurations might provide new approaches to energy storage and power generation. Engineered gravitational fields could lead to revolutionary materials with programmable inertial properties. These applications remain highly speculative, but they illustrate why warp drive research is attracting interest from fields far beyond aerospace engineering. The fundamental principles underlying spacetime manipulation could transform our understanding of physics and enable technological capabilities we can barely imagine today. The timeline for practical warp drive development remains highly uncertain and probably extends decades or centuries into the future. The challenges involved in exotic matter creation, precise spacetime engineering, and quantum mechanical stability are formidable by any measure. Even the most optimistic assessments suggest that working prototypes would require scientific and technological advances far beyond our current capabilities. Yet the theoretical foundations are becoming increasingly solid with each passing year. Advanced computational methods allow researchers to explore warp drive geometries with unprecedented mathematical precision. Experimental techniques provide new insights into quantum effects in curved spacetime. Our understanding of exotic matter, spacetime engineering, and the fundamental structure of reality continues to deepen. The field has transformed from Alcubierre's original mathematical curiosity into a legitimate research area that bridges theoretical physics with practical engineering considerations. Whether humanity will ultimately master the techniques needed to manipulate spacetime for faster-than-light travel remains an open question. But we're developing the scientific foundation needed to answer it definitively. The quest to understand warp drive physics is pushing us toward deeper comprehension of reality's most fundamental principles. Even if practical, faster-than-light travel proves impossible, the journey of investigation is expanding our knowledge of spacetime, quantum mechanics, and the relationship between matter and geometry in ways that will likely yield profound insights about the nature of existence itself. The nature of existence itself. As we delve deeper into the mathematical architecture of spacetime manipulation, we encounter concepts that challenge every assumption we've ever held about the nature of reality itself. The Alcubierre metric isn't just another equation gathering dust in physics journals. It's a precise mathematical blueprint for reshaping the fundamental structure of the universe, a cosmic construction manual that tells us exactly how space and time would need to bend to carry us between distant stars. To understand the profound elegance of this metric, imagine spacetime as an infinite ocean, with waves that can be shaped and directed by those who understand the underlying currents. The Alcubierre metric describes how to create a very special kind of wave, one that carries objects faster than light, without ever requiring them to move through space in the conventional sense. This isn't science fiction, hand-waving about mysterious faster-than-light engines. This is rigorous mathematics derived directly from Einstein's field equations, the same equations that describe how black holes warp spacetime and how GPS satellites must account for gravitational time dilation. The mathematical beauty of the Alcubierre metric lies in its geometric precision. When you work through the tensor calculus, what emerges is a description of spacetime that curves in three distinct regions. At the front of what we call the warp bubble, space itself contracts, compressing distances and bringing faraway destinations closer. At the rear, space expands, stretching the fabric of reality and pushing the point of origin farther away. And in the middle, within the bubble itself, space-time remains completely flat and undisturbed. This three-zone structure creates what physicists call a coordinate singularity, a mathematical feature where the normal rules of distance and time measurement break down in precisely controlled ways. From inside the warp bubble, you would measure distances and time intervals exactly as you would in normal flat space-time. But from outside, observers would witness something that appears to violate every principle of special relativity as they watch matter crossing vast distances faster than light could traverse the same space. The metric describes this phenomenon through what mathematicians call a foliation of spacetime, essentially slicing four-dimensional spacetime into three-dimensional spatial sections in ways that preserve causality within each slice while allowing apparent faster-than-light motion when viewed across different slices. This mathematical framework sidesteps the paradoxes that typically arise from faster-than-light travel scenarios because the spacecraft never actually exceeds the speed of light relative to its local spacetime environment. But translating mathematical elegance into physical reality requires us to master what might be the most challenging engineering problem in the history of science. Spacetime engineering demands that we learn to manipulate the energy-momentum tensor, the mathematical object that describes how matter and energy are distributed throughout the universe. Einstein's field equations tell us that the curvature of spacetime is directly proportional to this energy-momentum distribution. If we want to create specific types of spacetime curvature, we must arrange matter and energy in precisely corresponding configurations. This is where the concept of exotic matter becomes absolutely crucial to any practical implementation of warp drive technology. The spacetime curvature described by the Alcubierre metric cannot be produced by any form of ordinary matter or energy that we observe in nature. Stars, planets, black holes, electromagnetic radiation, dark matter, even antimatter all have positive energy density and create attractive gravitational effects that curve spacetime in the wrong direction for warp drive applications. Exotic matter represents something far more fundamental than simply rare or expensive materials. We're talking about substances with negative energy density, meaning they contain less energy than completely empty space itself. This might sound impossible until you realize that quantum mechanics already provides examples of such phenomena. The quantum vacuum isn't truly empty, but seethes with virtual particle pairs constantly appearing and disappearing. Under certain circumstances, it's possible to create regions with fewer virtual particles than the normal vacuum state, resulting in negative energy density. The gravitational effects of exotic matter would be unlike anything in our everyday experience. Instead of attracting other matter gravitationally, exotic matter would repel it. Instead of bending light rays inward like ordinary matter, it would bend them outward. Most importantly, for warp drive applications, it would curve spacetime in exactly the manner needed to create the expanding and contracting regions described by the Alcubierre metric. The energy requirements for creating sufficient quantities of exotic matter initially made warp drives seem completely impossible from an engineering perspective. When Alcubierre first calculated how much exotic matter would be needed to create a warp bubble large enough for practical spacecraft, the numbers defied comprehension. We're talking about negative energy densities, equivalent to the mass energy of entire solar systems, distributed with incredible precision throughout complex three-dimensional geometries. These weren't pessimistic estimates based on inefficient engineering approaches. They were fundamental requirements derived directly from the mathematics of general relativity. The Alcubierre metric specifies exactly how much spacetime curvature is needed to achieve faster-than-light travel, and Einstein's field equations tell us precisely how much exotic matter would be required to create that curvature. There's no way to negotiate with these mathematical requirements or find clever shortcuts without changing the basic physics. The breakthrough that transformed warp drives from impossible to merely extraordinarily difficult came through geometric optimization of the warp bubble configuration. Chris van den Broek realized that the size and shape of the warp bubble could be engineered for maximum efficiency, dramatically reducing the exotic matter requirements through clever spacetime architecture. Van den Broek's insight involved creating what physicists call a thin-shell warp drive, where most of the exotic matter is concentrated in a narrow boundary layer surrounding a much smaller interior region. Through careful manipulation of the spacetime geometry, this design creates a bubble that appears relatively small from the outside, but contains significantly more interior volume than its external dimensions would suggest. This dimensional manipulation, achieved through precise control of spacetime curvature, reduced exotic matter requirements by factors of billions or even trillions. Harold White's subsequent refinements pushed the energy requirements even lower through dynamic field modulation. His oscillating warp drive concept proposes rapidly pulsing the exotic matter distribution on and off, creating the illusion of continuous, faster-than-light motion through carefully timed intermittent effects. These calculations suggest that exotic matter requirements might be reduced to thousands of tons, rather than solar masses, bringing warp drives into the realm of theoretical possibility for sufficiently advanced civilizations. But these optimizations have sparked intense scientific debates about whether such refined warp drive designs could actually function in practice. The quantum mechanical properties of exotic matter introduce complications that weren't apparent in classical general relativistic analyses. Quantum field theory imposes strict constraints on how much negative energy can exist in any region of space, and for how long it can persist. The quantum inequality theorems, developed by physicists studying the fundamental limits of negative energy, suggest that nature prevents the creation of large-scale stable exotic matter configurations. These mathematical results don't absolutely prohibit exotic matter, but they do indicate that maintaining coherent warp fields might require overcoming quantum mechanical instabilities that could cause warp bubbles to collapse within microseconds of formation. Some physicists argue that these quantum constraints represent insurmountable barriers to practical warp drive development. They suggest that any attempt to create macroscopic quantities of exotic matter would be automatically frustrated by virtual particle fluctuations and quantum corrections to the classical spacetime geometry. According to this view, the universe has built-in protections against exotic matter accumulation that make warp drives physically impossible, regardless of our technological capabilities. Other researchers challenge these pessimistic interpretations by pointing to natural phenomena that demonstrate controllable negative energy effects. The Casimir effect, observed in countless laboratory experiments, proves that regions of negative energy density can be created and maintained between closely spaced, conducting plates. While these effects operate on microscopic scales, they demonstrate that exotic matter isn't merely a mathematical abstraction, but represents real physics that can be manipulated under appropriate conditions. Recent advances in metamaterial engineering and quantum field manipulation suggest possible pathways towards scaling up Casimir-like effects to larger dimensions. By creating precisely structured materials that control electromagnetic field configurations in unnatural ways, researchers might be able to generate and stabilize negative energy densities on scales approaching those needed for warp drive applications. The causality implications of faster-than-light travel add another dimension to these scientific controversies. Einstein's relativity demonstrates that faster-than-light travel could enable communication with the past under certain reference frame configurations, potentially creating logical paradoxes that threaten the consistency of physical law. If you can travel faster than light, you might be able to arrive at your destination before you left, or send messages to events that occurred in your own past. Stephen Hawking proposed the chronology protection conjecture to address these concerns, suggesting that unknown physical principles automatically prevent the creation of closed time, like curves that would allow paradoxical time travel. According to this idea, quantum effects or other natural mechanisms would intervene to prevent warp drive operation whenever it might lead to causality violations. Some physicists view these causality concerns as fundamental barriers that make faster-than-light travel impossible in principle. They argue that the universe must have built-in safeguards against paradox creation that would prevent warp drives from functioning, even if all the energy and exotic matter requirements could somehow be satisfied. Others contend that causality problems might resolve themselves through deeper understanding of quantum gravity and the relationship between space-time geometry and information theory. They point out that many revolutionary technologies initially appeared to violate established physical principles before we developed more complete theoretical frameworks to understand them properly. The quantum mechanical aspects of warp drive physics introduce mathematical complexities that push the boundaries of current theoretical understanding. When you attempt to incorporate quantum field theory effects into the classical Alcubierre geometry, the calculations become extraordinarily intricate. Virtual particle creation, vacuum polarization effects, and quantum corrections to spacetime curvature all play roles that could either stabilize or destabilize warp bubble formation. Some researchers suggest that quantum effects might actually assist warp drive operation rather than preventing it. The dynamic Casimir effect, which occurs when boundary conditions change rapidly, might provide mechanisms for generating exotic matter as the warp field forms and evolves. Instead of requiring pre-existing exotic matter supplies, a properly designed warp drive might be able to bootstrap itself by using the changing spacetime geometry to create its own exotic matter distribution. These quantum considerations are driving theoretical research toward increasingly sophisticated mathematical models that attempt to unify general relativistic spacetime curvature with quantum field theory in curved backgrounds. The resulting equations are so computationally intensive that they require supercomputer simulations to solve, pushing the limits of both theoretical physics and applied mathematics. Experimental investigations of warp drive physics are gradually transitioning from pure mathematical speculation toward laboratory studies of relevant physical principles. While we cannot yet create macroscopic warp fields, researchers can investigate quantum effects that might be applicable to exotic matter production and spacetime manipulation on smaller scales. Precision measurements of Casimir forces are revealing subtle details about how quantum fields behave in engineered geometries with rapidly changing boundary conditions. These experiments are uncovering effects that weren't predicted by early theoretical models, suggesting that our understanding of quantum field dynamics in curved spacetime geometries remains incomplete. High-energy particle accelerator experiments are exploring energy regimes where exotic matter signatures might become detectable. While these facilities cannot produce the massive quantities of exotic matter needed for spacecraft propulsion, they can test whether the fundamental physics underlying exotic matter creation is consistent with observed particle interactions and field theory predictions. Gravitational wave observatories are providing unprecedented precision measurements of spacetime curvature propagation and how gravitational fields interact with matter under extreme conditions. These observations test general relativity in regimes far beyond laboratory capabilities and might eventually detect signatures of natural spacetime engineering if such phenomena occur in astrophysical environments. The technological implications of mastering spacetime engineering extend far beyond interstellar transportation. Learning to create and manipulate exotic matter could revolutionize approaches to energy generation, materials science, and quantum-scale matter manipulation. If we can engineer spacetime geometry with precision, we might develop capabilities that appear magical by contemporary standards. Controlled spacetime curvature could enable creation of regions with modified temporal flow, where industrial processes could be accelerated or decelerated relative to external reference frames. Exotic matter configurations might provide revolutionary approaches to energy storage by creating pockets of negative energy density that could be tapped for power generation. Engineered gravitational fields could lead to materials with programmable inertial properties that respond differently to acceleration in various directions. These applications remain highly speculative, but they illustrate why warp drive research attracts interest from scientific fields far removed from aerospace engineering. The fundamental principles underlying spacetime manipulation could transform our understanding of physics and enable technological capabilities that we can barely conceptualize with current knowledge. The timeline for practical warp drive development remains highly uncertain and likely extends many decades or centuries into the future. The scientific challenges involved in exotic matter creation, precise spacetime geometry control, and quantum mechanical stability management are formidable by any reasonable measure. Even optimistic projections suggest that working prototypes would require scientific breakthroughs and technological capabilities far beyond anything currently achievable. Nevertheless, the theoretical foundations continue solidifying with each year of research progress. Advanced computational methods allow investigation of warp drive geometries with unprecedented mathematical precision. Experimental techniques provide increasingly detailed insights into quantum field behavior in curved spacetime environments. Our understanding of exotic matter physics, spacetime engineering principles, and fundamental reality structure continues deepening through sustained scientific investigation. The field has evolved from Alcubierre's original mathematical curiosity into legitimate research that bridges theoretical physics with engineering applications. Government agencies, universities, and private research institutions worldwide are investing resources in understanding whether the universe permits the kinds of spacetime manipulation that warp drive technology would require. This research program is pushing scientific understanding toward more complete comprehension of reality's most fundamental operating principles. Whether humanity will ultimately develop practical, faster-than-light travel capabilities remains an open question, but the investigation process is expanding our knowledge of spacetime, quantum mechanics, and matter geometry relationships in ways that will likely yield profound insights regardless of specific warp drive outcomes. The quest to understand spacetime engineering represents one of the most ambitious scientific endeavors in human history, challenging us to master forces that operate at the very foundation of physical existence. As we continue probing the mathematical structures that govern space, time, matter, and energy, we edge closer to answering whether the universe will permit us to become architects of reality itself, reshaping the cosmic stage upon which all existence plays out according to our deepest aspirations and most audacious dreams. The mathematical framework that makes all of this possible rests on what physicists call the stress-energy tensor, a fundamental component of Einstein's field equations that describes how matter and energy warp the fabric of spacetime itself. When Alcubierre first derived his metric, he wasn't simply playing with abstract mathematics. He was solving Einstein's equations backward, starting with the desired spacetime geometry and working out what kind of matter and energy distribution would be needed to create it. This reverse engineering approach revealed something profound about the relationship between matter and spacetime curvature. Instead of observing how existing matter naturally curves space and time, Alcubierre asked a different question entirely. What if we could design the curvature first and then figure out what kind of matter would be needed to produce it? This shift in perspective opened up possibilities that had never been seriously considered in the context of faster-than-light travel. The stress-energy tensor that emerges from this analysis describes matter with properties so unusual that it challenges our fundamental understanding of what substances can exist in our universe. We're not talking about materials that are simply rare or difficult to synthesize. We're describing matter that behaves in ways that seem to violate every intuitive notion we have about how physical objects should interact with gravity and electromagnetic fields. When you examine the mathematical requirements closely, what becomes clear is that the Alcubierre drive demands materials with negative energy density distributed in precise, three-dimensional patterns throughout the warp bubble geometry. This negative energy density isn't just a theoretical curiosity, it's an absolute requirement that cannot be avoided or substituted with any form of ordinary matter, no matter how exotic or energetic. To understand why this matters so profoundly, consider what negative energy density actually means in physical terms. Ordinary matter, from hydrogen atoms to neutron stars, has positive energy density relative to the quantum vacuum. This positive energy creates the attractive gravitational effects we observe throughout the universe. Planets orbit stars, galaxies hold together, and massive objects bend light inward, because matter consistently produces attractive space-time curvature. Negative energy density matter would do the exact opposite. It would create repulsive gravitational effects, pushing other matter away rather than attracting it. Light rays passing near such matter would bend outward instead of inward. Most crucially, for warp drive applications, this exotic matter would curve space-time in precisely the manner needed to create the contracting space at the front of the warp bubble and the expanding space at the rear. The challenge of creating macroscopic quantities of such exotic matter represents one of the most daunting engineering problems ever conceived. When researchers first calculated the energy requirements for an Alcubierre drive, the numbers were so large they seemed to mock the very concept of practical implementation. We're talking about exotic matter equivalent to the mass energy of multiple solar systems, arranged in configurations more precise than anything humans have ever attempted to build. These energy requirements aren't based on inefficient technology or poor engineering design. They emerge directly from the fundamental physics of space-time curvature as described by general relativity. The amount of exotic matter needed is determined by how much space-time must be warped to achieve the desired faster-than-light effect. There's no way to negotiate with these requirements or find clever shortcuts without abandoning the basic principles that make warp drives theoretically possible. The apparent impossibility of meeting these energy demands sparked a wave of research into alternative warp bubble geometries that might achieve similar results with more manageable resource requirements. The key insight came from recognizing that the efficiency of a warp drive depends critically on the detailed shape and size of the space-time distortion it creates. Van den Broek's breakthrough involved redesigning the warp bubble to concentrate most of the exotic matter in a thin shell surrounding a much smaller interior volume. This approach takes advantage of a peculiar property of curved space-time geometry, where the interior of a region can be larger than its exterior dimensions would suggest when viewed from normal flat space-time. The mathematical description of this optimized geometry involves what physicists call a thin shell approximation, where the exotic matter is concentrated in a narrow boundary layer rather than being distributed throughout the entire warp bubble volume. This concentration dramatically reduces the total amount of exotic matter required while maintaining the same faster-than-light travel capabilities. Harold White's subsequent refinements push these optimizations even further by proposing dynamic warp field modulation. Instead of maintaining constant exotic matter densities throughout the journey, his oscillating warp drive concept involves rapidly pulsing the field, strength on and off, in carefully choreographed sequences. This approach exploits relativistic effects to create the appearance of continuous faster-than-light motion, while actually requiring exotic matter only during brief intervals. The mathematics underlying these dynamic systems are extraordinarily complex, involving differential equations that describe how space-time curvature changes as the exotic matter distribution oscillates. The calculations suggest that pulsed warp drives might reduce exotic matter requirements to levels that, while still enormous by contemporary standards, are no longer equivalent to converting entire solar systems into exotic matter. These theoretical advances have generated intense scientific debate about whether optimized warp drives could actually function as described. The quantum mechanical properties of exotic matter introduce complications that weren't apparent in the original classical general relativistic analysis. Quantum field theory places fundamental constraints on negative energy that might prevent the stable configurations required for warp drive operation. The quantum inequality theorems represent some of the most sophisticated mathematical results in modern physics, describing precisely how much negative energy can exist in any region of spacetime, and for how long it can persist before quantum fluctuations destroy the configuration. These theorems don't absolutely prohibit exotic matter, but they do suggest that maintaining coherent warp fields might require overcoming quantum instabilities that operate on incredibly short timescales. According to some interpretations of these quantum constraints, any attempt to accumulate the exotic matter needed for warp drives would trigger automatic quantum corrections that would dissipate the negative energy before it could be effectively utilized. Virtual particle creation, vacuum polarization effects, and quantum field fluctuations would conspire to prevent the formation of stable macroscopic exotic matter structures. Other physicists challenge these pessimistic conclusions by pointing to natural phenomena that demonstrate controllable negative energy effects on laboratory scales. The Casimir effect, which has been measured with extraordinary precision in countless experiments, proves that regions of negative energy density can be created and maintained between conducting surfaces under appropriate conditions. The Casimir effect arises from quantum field fluctuations in the electromagnetic vacuum between closely spaced metal plates. By constraining which virtual photon modes can exist in the gap between the plates, this configuration creates a region with lower energy density than the surrounding vacuum, resulting in measurable attractive forces that demonstrate the reality of negative energy. Recent research into metamaterials and engineered quantum systems suggests that Casimir-like effects might be scalable to larger dimensions through careful manipulation of electromagnetic boundary conditions. By creating materials with precisely controlled optical and electromagnetic properties, researchers might be able to generate regions of negative energy density on scales approaching those needed for exotic matter applications. Some theoretical proposals involve using arrays of metamaterial structures to create what physicists call artificial vacuum states, regions where quantum field configurations are modified in ways that produce effective negative energy densities. These approaches would require extraordinary precision in materials engineering and quantum state control, but they offer potential pathways toward exotic matter production that don't require completely new physics. The debates surrounding warp drive feasibility extend beyond just the technical challenges of exotic matter creation. Fundamental questions about causality and the nature of faster-than-light travel raise concerns that go to the heart of our understanding of spacetime and information theory. Einstein's special relativity demonstrates that faster-than-light travel could enable communication with the past under certain reference frame configurations. If you can travel faster than light between 2 points, there exist inertial reference frames where you arrive before you left, potentially allowing you to influence events in your own past. This possibility creates logical paradoxes that seem to threaten the consistency of physical law itself. The grandfather paradox, familiar from science fiction, illustrates the conceptual difficulties. If faster-than-light travel allows time travel to the past, you might theoretically be able to prevent your own birth, creating a logical contradiction that appears to make such travel impossible. These causality concerns have led some physicists to argue that the universe must have built-in protections against faster-than-light travel, regardless of technological capabilities. Stephen Hawking's chronology protection conjecture proposes that unknown physical mechanisms automatically prevent the creation of closed time, like curves, that would allow paradoxical time travel. According to this idea, quantum effects or other natural processes would intervene to sabotage any attempt to build devices that could cause temporal paradoxes, including potentially warp drives that might enable faster-than-light travel. The mathematical formulation of chronology protection involves subtle aspects of quantum field theory in curved spacetime that are not fully understood. Some calculations suggest that quantum fluctuations become infinitely large near the boundaries of regions where closed time-like curves might form, effectively creating impenetrable barriers that prevent paradox creation. Other analyses indicate that quantum effects might stabilize such regions rather than destroying them. These theoretical uncertainties reflect deeper questions about the relationship between quantum mechanics and general relativity that remain unresolved despite decades of intensive research. The quantum theory of gravity, which would be needed to fully analyze warp drive physics, doesn't exist in complete form, leaving crucial aspects of spacetime engineering in the realm of educated speculation rather than established science. Some physicists argue that causality concerns, while intellectually fascinating, shouldn't prevent research into faster-than-light travel technologies. They point out that many revolutionary discoveries initially appeared to violate established principles before more complete theoretical frameworks revealed how apparent contradictions could be resolved. The history of physics is filled with examples of seemingly impossible phenomena that became routine once we developed better understanding of the underlying principles. The quantum mechanical aspects of warp drive operation introduce additional layers of complexity that weren't apparent in Alcubierre's original classical analysis. When you attempt to incorporate quantum field theory effects into spacetime engineering calculations, the mathematics become extraordinarily sophisticated, requiring advanced computational methods that push the boundaries of theoretical physics. Quantum corrections to the classical Alcubierre metric involve calculating how virtual particle creation and annihilation processes are affected by rapidly changing spacetime curvature. These effects could either stabilize warp bubbles by providing additional sources of exotic matter through quantum field manipulation, or destabilize them by introducing fluctuations that prevent coherent warp field formation. The dynamic Casimir effect, which occurs when electromagnetic boundary conditions change rapidly, represents one possible mechanism for generating exotic matter during warp bubble formation. As the spacetime geometry evolves, the changing field configurations might spontaneously produce regions of negative energy density that could supplement externally supplied exotic matter, or potentially eliminate the need for exotic matter entirely. These quantum processes operate on time scales and energy scales that are extremely difficult to analyze using current theoretical methods. The calculations require sophisticated techniques from quantum field theory in curved spacetime, an area of physics that remains mathematically challenging even for relatively simple geometries. The complex time-dependent spacetime configurations involved in warp drive operation push these methods to their absolute limits. Experimental investigations of warp drive physics are necessarily limited to studying the underlying physical principles rather than creating actual warp bubbles. However, precision measurements of quantum effects in curved spacetime geometries are providing valuable insights into whether the theoretical foundations of spacetime engineering are consistent with observed physics. Laboratory studies of the Casimir effect under various geometric configurations are revealing details about how quantum fields respond to rapidly changing boundary conditions. These experiments test predictions of quantum field theory in curved spacetime and might eventually detect signatures of exotic matter production through quantum field manipulation. Particle accelerator experiments are exploring energy regimes where quantum gravity effects might become observable. While these facilities cannot directly test warp drive concepts, they can investigate whether the fundamental physics underlying exotic matter creation is consistent with the standard model of particle physics and general relativity. Gravitational wave detectors are providing unprecedented measurements of spacetime dynamics and how gravitational effects propagate through the universe. These observations test general relativity under extreme conditions and might reveal previously unknown aspects of spacetime physics that could be relevant to engineering applications. The technological implications of successful spacetime engineering would revolutionize far more than just interstellar transportation. Mastering the creation and manipulation of exotic matter would open up possibilities for energy generation, materials science, and quantum technology that we can barely imagine with current knowledge. Controlled spacetime curvature could enable the creation of regions where time flows at different rates relative to the external environment, potentially allowing industrial processes to be accelerated or decelerated as needed. Manufacturing could be completed in compressed time frames, or delicate processes could be slowed down to allow unprecedented precision and control. Exotic matter configurations might provide revolutionary approaches to energy storage and generation by creating stable pockets of negative energy density that could be harvested for power production. These systems could potentially store enormous amounts of energy in compact volumes or extract energy from quantum field fluctuations in ways that don't violate conservation laws. The timeline for practical spacetime engineering remains highly speculative and likely extends many decades or centuries into the future. The scientific challenges involved in exotic matter production, quantum field manipulation, and precision spacetime geometry control represent some of the most difficult problems in physics. Even the most optimistic assessments suggest that working warp drive prototypes would require breakthrough discoveries and technological capabilities far beyond anything currently achievable. However, the theoretical foundations are becoming increasingly sophisticated as research progresses. Advanced computational methods allow detailed investigation of warp drive geometries and exotic matter configurations. Experimental techniques provide growing insight into quantum field behavior under extreme conditions. Our understanding of spacetime physics, exotic matter properties, and the fundamental structure of reality continues expanding through sustained scientific investigation. The field has evolved from mathematical curiosity into legitimate research that attracts interest from government agencies, universities, and private institutions worldwide. Whether humanity will ultimately master the techniques needed for practical spacetime engineering remains uncertain, but the scientific foundation for answering this question definitively is being constructed through rigorous, theoretical, and experimental work. This research represents one of the most ambitious scientific endeavors in human history, challenging us to understand and potentially control the forces that operate at the very foundation of physical existence. As we continue probing the mathematical structures that govern space, time, matter, and energy, we approach the possibility of becoming true architects of reality, capable of reshaping the cosmic stage itself according to our deepest aspirations for exploration and discovery among the stars. But even as we stand at the threshold of these profound possibilities, we must confront the sobering reality that spacetime engineering might represent the ultimate test of human scientific ingenuity. The Alcubierre metric, elegant as it appears on paper, demands that we solve problems so fundamental they challenge the very boundaries between the possible and impossible. Think about what we're really asking the universe to permit. We want to grab the fabric of spacetime itself, stretch it in some places, compress it in others, and create pockets of engineered reality that behave according to our specifications rather than natural law. This isn't simply building better rockets or discovering new materials. We're talking about becoming cosmic architects who can redesign the stage upon which all physics plays out. The mathematical precision required for this kind of spacetime engineering boggles the mind. The Alcubierre metric specifies exactly how spacetime curvature must vary throughout the three-dimensional volume of the warp bubble. We're not talking about rough approximations or getting close enough for practical purposes. The geometry must be precisely correct to within tolerances that make the most advanced manufacturing seem crude by comparison. Consider the spatial gradients involved in creating the warp bubble boundary. The transition from normal flat spacetime to the exotic curved geometry inside the bubble must occur over distances measured in meters or kilometers, yet the curvature changes involved are comparable to those found near black holes or neutron stars. We need to create and maintain these extreme spacetime distortions using exotic matter distributions that remain stable despite quantum mechanical forces trying to tear them apart. The engineering challenges extend far beyond just creating exotic matter in sufficient quantities. We need to shape that exotic matter into three-dimensional configurations that match the mathematical requirements of the Alcubierre metric with extraordinary precision. Think about trying to sculpt with a material that has negative mass, repels itself gravitationally, and interacts with electromagnetic fields in ways that defy intuition. Every piece of exotic matter in the system affects every other piece through gravitational and quantum field interactions that must be calculated and controlled simultaneously. The control systems required for warp drive operation would need to monitor and adjust thousands of parameters in real time as the spacetime geometry evolves during acceleration, cruise, and deceleration phases. Unlike conventional spacecraft, where you can make course corrections gradually, warp drive systems would require instantaneous responses to maintain the delicate balance between expanding spacetime at the rear and contracting spacetime at the front of the bubble. Any deviation from the precise geometric requirements could cause catastrophic warp field collapse, potentially stranding the spacecraft in interstellar space or worse, creating uncontrolled spacetime distortions that could damage the fabric of reality itself. The safety margins for warp drive operation might be measured in parts per billion rather than the comfortable tolerances we're accustomed to in conventional engineering. These technical challenges become even more daunting when you consider the quantum mechanical environment in which warp drives would operate. The rapidly changing spacetime geometry creates conditions where virtual particles are constantly being created and destroyed at enormous rates. These quantum processes inject random fluctuations into the exotic matter distribution that must be compensated by active control systems operating faster than the quantum decoherence timescales. Some physicists have calculated that maintaining a stable warp bubble might require feedback control systems that can respond to quantum fluctuations in microseconds or even nanoseconds. This level of real-time quantum state control exceeds anything we've achieved in laboratory settings by many orders of magnitude. We would need quantum computers specifically designed for spacetime engineering applications, running algorithms that don't yet exist to control physics we don't fully understand. The energy infrastructure required to support warp drive operations presents another category of seemingly insurmountable challenges. Even the optimized designs that have reduced exotic matter requirements to theoretically manageable levels still demand energy sources far beyond anything in human experience. We're talking about power generation capabilities that dwarf the total energy output of contemporary civilization by factors of millions or billions. These energy requirements aren't just large numbers on paper. They represent fundamental constraints on what kinds of civilizations could realistically develop warp drive technology. You would need industrial capabilities that could harness the power output of entire stars, energy storage systems that could contain forces comparable to those in stellar cores, and power distribution networks that could deliver that energy with perfect efficiency to exotic matter manipulation systems. The economic implications alone suggest that warp drives, even if technically feasible, might remain forever beyond the reach of planet-bound civilizations. You might need to be a Kardashev Type 2 civilization, capable of harnessing the complete energy output of your home star, before warp drive development becomes economically viable. This requirement could explain why we haven't detected evidence of warp-capable aliens despite the vast number of potentially habitable worlds in our galaxy. Yet for all these challenges, the mathematical foundations of warp drive physics continue to solidify with each year of research. Advanced computer simulations are revealing subtle aspects of exotic matter behavior that weren't apparent in early analytical calculations. Researchers are discovering that certain configurations of exotic matter might be more stable than previously thought, while others that seemed promising turn out to violate quantum mechanical constraints. The field is also benefiting from unexpected connections to other areas of theoretical physics. Research into dark energy, the mysterious force driving the accelerating expansion of the universe, has revealed mathematical similarities to exotic matter that might provide alternative pathways to spacetime engineering. Some physicists speculate that learning to manipulate dark energy could eliminate the need for exotic matter entirely, though these ideas remain highly speculative. String theory and other approaches to quantum gravity are providing new mathematical tools for analyzing spacetime engineering problems. These advanced theoretical frameworks suggest that the relationship between matter, energy, and spacetime curvature might be more flexible than Einstein's classical general relativity indicates. If these quantum gravity theories prove correct, they might reveal previously unknown mechanisms for creating the spacetime distortions needed for warp drives. The experimental side of warp drive research is advancing through investigations of related phenomena that test the underlying physics in accessible laboratory settings. Researchers are studying how electromagnetic fields behave in rapidly changing geometric configurations, how quantum fields respond to time-dependent boundary conditions, and whether artificial negative energy states can be created and controlled using advanced materials. Some of the most promising experimental work involves precision measurements of the Casimir effect under dynamic conditions, where the spacing between metal plates changes rapidly. These experiments are revealing quantum field behaviors that weren't predicted by static calculations and might provide insights into how exotic matter could be generated during warp bubble formation and collapse. Metamaterial research is exploring whether carefully engineered structures can create effective negative energy densities by manipulating electromagnetic field configurations in unnatural ways. While these effects operate on microscopic scales, they demonstrate principles that might eventually be scalable to the macroscopic dimensions needed for spacecraft applications. The international scientific community studying these questions has grown from a handful of theorists working in isolation to research groups at major universities and government laboratories around the world. NASA continues funding preliminary studies into breakthrough propulsion concepts, including warp drives. The European Space Agency has acknowledged interest in revolutionary propulsion technologies that could enable interstellar exploration within human lifetimes. Private research institutions and aerospace companies are beginning to invest in fundamental research that could eventually lead to spacetime engineering capabilities. While practical applications remain decades or centuries in the future, the potential transformative impact of such technologies justifies long-term research investments that might not pay off for generations. The cultural and philosophical implications of warp drive development extend far beyond the technical challenges. If humanity eventually masters spacetime engineering, we would join what might be a very exclusive club of civilizations capable of reshaping reality according to their needs and desires. This technological transition could represent the most significant evolutionary leap in human history, transforming us from a planet-bound species to true citizens of the galaxy. The psychological impact of knowing that faster-than-light travel is possible, even if not yet practical, changes how we think about our place in the universe. Distance becomes less absolute when you realize that sufficiently advanced technology could make the nearest stars accessible within human lifetimes. The galaxy transforms from an impossibly vast collection of unreachable points of light into a potential neighborhood where exploration and discovery await those bold enough to attempt the journey. Yet these same possibilities force us to confront uncomfortable questions about the nature of intelligence and technological development throughout the cosmos. If warp drives are possible in principle, why haven't we detected evidence of alien civilizations using such technologies? The continued silence from space might indicate that the technical challenges we've been discussing represent barriers that few civilizations successfully overcome. Perhaps the exotic matter requirements, quantum mechanical instabilities, and energy demands create filters that eliminate most technological species before they can achieve interstellar capabilities. The universe might be littered with the remains of civilizations that understood warp drive physics perfectly but could never marshal the resources needed to implement the technology practically. Alternatively, successful warp-capable civilizations might develop in directions that make them effectively invisible to our detection methods. Species that can engineer spacetime might also be able to engineer their detectability, choosing to remain hidden from younger civilizations like ourselves. The galaxy could be teeming with advanced intelligence that deliberately avoids contact until newly emerged species demonstrate sufficient wisdom to use spacetime manipulation technologies responsibly. These considerations add urgency to current warp drive research efforts. We're not just investigating interesting physics or pursuing technological capabilities for their own sake. We're potentially working to solve problems that could determine whether human civilization has a future among the stars or remains forever confined to our single solar system. The next few decades will likely prove crucial for determining which path our species follows. Advances in quantum computing, materials science, and fundamental physics are providing new tools for attacking the theoretical and experimental challenges that have made warp drives seem impossible. We're approaching technological capabilities that might finally allow serious testing of exotic matter production and space-time manipulation concepts. As we stand at this crossroads between the scientifically impossible and the merely extraordinarily difficult, one thing becomes clear. The universe has written the rules that govern space, time, matter, and energy with mathematical precision. Whether those rules permit the kind of reality engineering that warp drives require remains the greatest open question in physics. The answer will determine not just the future of human space exploration, but our understanding of what intelligence can ultimately achieve in a cosmos that seems designed to challenge every assumption we make about the limits of the possible. The journey toward that answer continues in laboratories and theoretical studies around the world, driven by the recognition that we're investigating one of the most profound questions ever asked. Can conscious beings transcend the apparent limitations imposed by the speed of light and become architects of space-time itself? The mathematics suggest yes, but the universe has yet to reveal whether it will permit such audacious dreams to become reality. As we reach the culmination of our journey through the mathematics and physics of faster-than-light travel, we find ourselves confronting a profound realization about the nature of scientific progress itself. The story of warp drive research represents something far more significant than just another technological challenge. It embodies humanity's relentless drive to push beyond apparent limitations and explore possibilities that previous generations could never have imagined. The scientific debates surrounding warp drive feasibility have evolved into something resembling a cosmic courtroom where the laws of physics serve as both judge and jury. On one side, we have researchers who argue that the mathematical elegance of the Alcubierre metric represents a genuine loophole in the universe's speed limit. They point to the rigorous derivations from Einstein's field equations, the successful geometric optimizations that have reduced energy requirements, and the laboratory demonstrations of negative energy effects through the Casimir force. These optimists emphasize that science has repeatedly achieved what once seemed impossible. Heavier than air flight violated common sense until the Wright brothers proved otherwise. Quantum mechanics appeared to mock logic until it became the foundation for modern electronics. Nuclear fusion seemed like an impossible dream until we learned to harness the same processes that power the stars. From this perspective, warp drives represent the next chapter in humanity's ongoing conquest of natural limitations. But the skeptical voices carry equal weight in these discussions, armed with quantum inequality theorems and thermodynamic constraints that suggest the universe has built-in protections against exotic matter accumulation. They argue that the energy requirements, even after optimization, remain so astronomical that they place warp drives forever beyond the reach of any conceivable civilization. The quantum mechanical instabilities alone, they contend, would prevent stable warp bubble formation regardless of our technological sophistication. These debates reflect deeper philosophical questions about the relationship between mathematical possibility and physical reality. Just because we can write down equations that describe faster than light travel doesn't necessarily mean the universe permits such phenomena to exist. Mathematics has led us astray before, describing perfectly consistent systems that have no correspondence to physical reality. The resolution of these debates may ultimately depend on discoveries we haven't yet made about the fundamental nature of spacetime, quantum mechanics, and the relationship between matter and geometry. We're still missing crucial pieces of the puzzle, particularly a complete theory of quantum gravity that could definitively tell us whether exotic matter can exist in the stable macroscopic quantities that warp drives require. What makes this scientific uncertainty so compelling is that the stakes extend far beyond academic curiosity. If warp drives prove feasible, even in principle, they would represent the most transformative technology in human history. The ability to traverse interstellar distances within human lifetimes would fundamentally alter our species' relationship with the cosmos, transforming us from planetary prisoners into galactic explorers. The psychological impact alone would be revolutionary. Knowing that the stars are genuinely within reach would change how we think about our future, our purpose, and our place in the universe. Scientific missions that currently require multi-generational commitments could be completed within single careers. The search for extraterrestrial life would transition from remote sensing to direct exploration. The dream of establishing human colonies among distant worlds would shift from science fiction to engineering challenge. So where does this leave us on our cosmic journey through the mathematics of impossibility? We've travelled from Miguel Alcubierre's elegant equations through the bizarre realm of exotic matter, witnessed the fierce scientific debates that rage in physics departments worldwide, and confronted energy requirements that dwarf the output of entire stars. The Alcubierre metric stands before us like a cosmic riddle, mathematically perfect, yet potentially forever beyond our technological grasp. Tonight, you've seen how spacetime engineering could theoretically transform us from planetary wanderers into architects of reality itself. You've learned why exotic matter with its mind-bending negative energy density remains the holy grail that could unlock faster than light travel, and why creating even microscopic quantities pushes the boundaries of what physics allows. The scientific community remains beautifully divided between those who see warp drives as humanity's inevitable destiny and those who view them as elegant impossibilities. Perhaps that's exactly where we should be, standing at the edge of the unknown, armed with mathematics that hint at cosmic possibilities beyond our wildest dreams, yet humbled by the recognition that the universe guards its deepest secrets jealously. Whether we'll ever surf waves of curved spacetime between distant stars remains the greatest open question in physics. Until we meet again, on another voyage through the mysteries of existence, keep wondering, keep questioning, and remember that today's impossibilities have a curious habit of becoming tomorrow's realities.